Welcome to Developmental Biology. Today, we are exploring a crucial and fascinating topic called teratogenesis. We will uncover exactly how external environmental agents can disrupt the delicate, highly choreographed process of a developing embryo. By the end of this lesson, you will understand the biological mechanisms and the mathematical models that scientists and doctors use to predict risks and prevent birth defects. Let us start with a simple analogy. Imagine you are building a complex, beautiful house from scratch. If a massive storm hits while you are just pouring the concrete foundation, the entire structure will be fundamentally ruined, and it might even collapse. However, if that exact same storm hits months later when you are merely painting the bedroom walls, the damage will be minor and easily fixable. The development of a human baby inside the womb works in a very similar way. The timing of a biological disruption is absolutely everything when determining the severity of the outcome. Now that we understand why timing matters, let us formally define our topic. In developmental biology, teratogenesis refers to the complex process by which congenital malformations, or birth defects, are produced in a developing embryo. The term comes from the Greek words for monster and creation. A teratogen is any external environmental agent that causes these abnormalities. This could be a chemical drug, a virus, or even radiation. It is very important to note that unlike genetic mutations, which are inherited from the parent's DNA, teratogenic effects are strictly caused by these outside factors, interfering with normal development. To truly appreciate why this science is vital, we must look at history. In the late 1950s, a tragic real-world event occurred. Pregnant women were prescribed a mild sedative called thalidomide to combat morning sickness. Because the medical community did not yet fully understand teratogenesis, thousands of babies were born with severe limb deformities. This heartbreaking event forever changed how we test drugs. Today, the rigorous science of teratogenesis is exactly what allows doctors to safely advise pregnant women on what medications to avoid, preventing countless birth defects. Building on that historical context, let us look at the specific biological factors involved. While biology is often seen as purely descriptive, the likelihood and severity of a teratogenic event actually depend on three primary variables. First is the dose, or how much of the agent reaches the embryo. Second is the timing, meaning the exact developmental stage of the embryo when the exposure happens. And third is genetic susceptibility, which dictates how easily an individual's cells are disrupted. By identifying these three variables, we can begin to quantify the danger of any specific exposure. Now that we have identified the three variables, we can combine them into a mathematical framework. This formula calculates the teratogenic risk score, represented by R. It equals D times T times G. D stands for the dose of the teratogenic agent, usually measured in milligrams per kilogram. T represents the timing factor, which is a numerical multiplier that is highest during the critical embryonic period. Finally, G represents the genetic susceptibility factor, a baseline multiplier unique to each individual. If the dose increases, the overall risk increases proportionally. However, if the exposure happens outside the critical window, a low timing value can keep the total risk relatively small. Let us apply this formula to a practical scenario. Suppose a pregnant woman is accidentally exposed to 50 units of a chemical teratogen during week 4 of pregnancy. We are given a high timing factor of 0.9 and a standard genetic susceptibility of 1.2. We want to find the total risk score. We substitute these values into our equation. Multiplying the dose of 50 by the timing factor of 0.9 gives 45. Multiplying that by the genetic factor of 1.2 yields a final risk score of 54. This high number indicates a severe likelihood of major structural abnormalities because cells are rapidly dividing to form organs during this early window. Now, let us see what happens if the exact same exposure occurs much later. In scenario B, the exposure happens during week 20. The dose remains 50 and the genetic factor remains 1.2, but the timing factor drops significantly to 0.1 because week 20 is in the fetal period. Substituting these into our equation, 50 times 0.1 gives 5. Multiplying by 1.2 gives a final risk score of just 6. This score is 9 times lower than scenario A. It mathematically proves that timing is just as critical as dose. The baby might experience minor growth delays, but will likely avoid catastrophic structural defects. To visualize why the timing factor changes so drastically, let us look at this susceptibility graph. The horizontal axis represents the weeks of pregnancy, and the vertical axis shows the risk level. Notice the massive peak between weeks 3 and 8? This is the embryonic period, where organs are initially forming. Any disruption here causes major structural defects, which is why the curve is so high. After week 8, the curve drops steeply and flattens out for the remainder of the pregnancy. This is the fetal period. The organs have already formed and are merely growing in size, so the biological vulnerability is significantly reduced. This graph perfectly illustrates why doctors are most concerned about first trimester exposures. Moving beyond timing, another crucial concept in teratogenesis is the idea of a safe limit or threshold. Unlike cancer-causing agents, where even a single molecule might theoretically cause a mutation, teratogens usually require a minimum accumulation of damage before any physical defect is visible. This is because the developing embryo has an incredible capacity to repair minor cellular damage or replace a few dead cells. Therefore, a birth defect only occurs when the dose of the teratogen completely exceeds the embryo's natural ability to repair itself. This biological reality leads us to our next mathematical model. To quantify this repair capacity, we use the linear threshold equation. The severity of the birth defect, S, equals K times the quantity D minus D subscript T. Here, D is the actual dose the embryo receives, and D subscript T is the threshold dose, which is the maximum amount the embryo can perfectly repair. The term inside the parentheses represents the excess toxic dose. The variable K is a constant representing the specific toxicity of the chemical. It acts as an amplifier for the damage. If the actual dose is less than or equal to the threshold, the severity is 0, meaning the baby develops perfectly normally. Let us see how this threshold equation works in practice. Suppose a pregnant patient accidentally consumes 50 milligrams of a drug. Laboratory tests show the embryo can safely repair up to 30 milligrams, so our threshold is 30. The drug's toxicity constant is 2.5. We want to find the severity score. First, we see that 50 is greater than 30, so a defect will occur. We substitute our values into the equation. Subtracting the 30 milligram threshold from the 50 milligram actual dose leaves an effective toxic dose of 20 milligrams. This is the amount that overwhelmed the repair mechanisms. Multiplying this 20 by the toxicity constant of 2.5 gives a final severity score of 50, indicating a significant birth defect. We have covered a lot of ground today. To summarize, teratogenesis is the study of how external environmental agents disrupt the highly choreographed process of embryonic development. We learned that the impact of a teratogen is not just about toxicity. It is heavily dependent on the exact timing of the exposure and whether the dose crosses the embryo's natural repair threshold. By mastering these biological concepts and mathematical models, scientists and doctors can establish safe exposure limits and protect the health of developing babies worldwide. You now have a solid understanding of how birth defects occur